Hello, everyone. I'm Manasadevi Thirugnanasambandam. I'm a research faculty at IUCAA, and I'm an optical experimental physicist by training. And my research interests are mostly in lasers and optical systems for precision measurement. Here at IUCAA, I work as part of the LIGO India team at IUCAA, and I share responsibilities with the rest of the team and the other nodal institutes building up LIGO India for establishing the upcoming LIGO India detector. So I think this is probably the last talk of our summer school, and after our talk, our director or someone of the organizers will be talking to you as well. So please stay on even after the talk. And so let's proceed our discussion for the next hour. I believe you've already heard a few talks about gravitational wave detectors, including the one just before this by Dr. Suresh Doravari. And what I'm going to talk about is more detailed, more into the details of the skeletal structure of the interferometer itself. And before that, I'm just going to turn off my video so that it's not interfering with the slides that you see. So what do you see? So we'll start a little bit of a background. I know you've heard it many times, but this kind of gives the motivation and sort of background how the skeletal structure of an interferometer came up for gravitational wave detection. So it dates back to the time when there was a conflict between the Newtonian and Einstein way of defining gravity. And what you see is, so as per Newton, gravity is actually a force. And although the Newton's laws, they describe the effects of gravity beautifully, the Newton's laws do not propose a mechanism as to how gravity worked. So what happened after that is Einstein came up with his theory of relativity. And what he used to describe gravity is as calling it a fundamental part of the structure of the universe itself. And it is actually a curvature of the space-time fabric. And according to which it is as this fabric curves or twists or ripples when the objects move around it, that is how you can define a mechanism as to how gravity worked. So this actually could explain a lot of the things that Newton's laws could not explain. So if you were to assume such an object in the space-time fabric moving around, the animation here will describe how that object will distort the space-time fabric around it. And this is the beginning of how you can explain the way gravity worked. So John Wheeler put it in a very simple expression. He said, space-time grips mass and tells it how to move around, and mass tells space-time how to curve. So if you have to describe Einstein's equation, through Einstein's equation, whenever such a matter moves or changes configuration or jostles or rotates around it and causes a change in the gravitational field, the changes actually propagate in the space-time curvature as ripples. And these ripples are what we call gravitational waves. This is very important because gravity and gravitational waves are slightly different. The way that you define them are very different. Gravitational wave comes from a gravitational field change, and they are ripples in the space-time that we can measure. So now if you have to look at a gravitational wave frequency spectrum, like electromagnetic waves, we can put the gravitational wave frequency spectrum as well. And in this frequency spectrum, as you see it, you see actually the different sources that are that are listed on the left-hand side, and you see the sort of detectors that are being used that can be typically detect such kind of sources on the right-hand side. So what we are more interested is in the ground-based interferometers, and we will be looking at gravitational waves in the frequency of hertz to a maximum of like a few kilohertz. That's all the interferometers can detect. So, and the phenomenon that we can detect, the sources that we can detect are mostly binary neutron stars and binary black holes. You've heard a lot about the astrophysics of this in our previous talks. So now, if you look at the existing gravitational wave detectors, we see that in this picture, you see that the terrestrial gravitational wave detectors are all confined to the far right. Sorry. And you see the terrestrial detectors that are named in here are the GEO 600, LIGO, Virgo, which are the earlier versions of the now existing advanced LIGO and advanced Virgo. We also have Kagra in here that joins the detector in Japan that also falls under this family of detectors. So if we want to build an gravitational wave detector, it is important to know what the effect of the physical effect of a gravitational wave. So if we consider a ring of freely falling test masses, and you have a gravitational wave that passes through the ring would actually get stretched and squeezed as shown in this image, depending on the polarization of the gravitational wave that affects it. As you can see, one of them is a plus polarization and the other one is actually a cross polarization. So this is how a gravitational wave would affect a freely falling test mass. It's important to know that this is the effect on a freely falling test mass, and our efforts go into realizing a freely falling test mass with gravitational wave detectors. So if you have an interferometer, a simple Michelson interferometer, which is actually, which has a laser, and then it has a beam splitter in the center that splits the beam into two orthogonal directions. And the beam traverses in two orthogonal directions, hits the end mirrors, and then comes back and recombines at the beam splitter. And what we see here is what we call the dark port of the interferometer. Depending on the constructive or destructive interference of the recombined laser field, you can see that you can see either a bright or a dark fringe. So now if you assume the two end mirrors to be objects on the ring that you saw in the earlier picture, if the end mirrors are freely falling test masses, the interferometer will be stretched and squeezed, as you see in this animation, causing an optical phase change along the path it traverses, giving rise to dark or bright fringe at the dark port of the interferometer. So a gravitational wave signal can be measured as the optical phase in an interferometer. So now, if we were to look at, we know that a Michelson interferometer can help us sense a gravitational wave. But it's also important to know that the interferometer does not behave like a typical telescope. Its more close, its behavior is more close to an antenna. And the response of the interferometer to gravitational waves of the two polarizations that we considered from various directions can be seen in this picture as more of a lobed structure. And this is crucial to understand because the directivity of a single detector that we build is going to be very less, which means that You cannot use a single detector to identify a source or localize a source effectively. So the more detectors that we have, the better we can localize the source in the sky. And the idea of using an interferometer for gravitational wave detection led to the birth of LIGO. As you can see in this picture that on the left-hand side, you can see that there is a laser and you can see there is an interferometer. So in here, it is said that this is one of the earlier proposals that was submitted for building the LIGO detectors. And you can see it's called a proposed antenna. And a Michelson being used to detect a gravitational wave is actually a flawless method of detection. So this brought to the birth of LIGO, the two detectors that we have right now at Livingston and Hanford. So we know that we are going to use a Michelson interferometer to build a gravitational wave detector. But in reality, the skeleton of the detector that we use today is not a simple Michelson. And today we will actually delve deep into understanding why we don't use just a simple Michelson, why we have to complicate things a little further. So in here, what you see is the picture of a simple interferometer. You have the laser. The electric field E0 is incident at the beam splitter, and then it gets split into two fields in the north and east. That's how it's named, E and N, if you're looking for the convention. And then it reflects back and comes and recombines at the photodetector. So if one of the arms, so in a typical Michelson, the arm lengths are equal. So if we consider a gravitational wave, stretching one of the arms, ME, the end mirror, by moving it by length delta L, then the pattern that you would see at the photodetector, the intensity pattern that you would see at the photodetector, will move across dark and bright fringes as seen in the plot below. And the strain in the detector, you can define a strain parameter H that will be a ratio of this length change over the length of the interferometer itself. If you have to calculate what H is, what is the strain that a typical gravitational wave will produce on a Michelson interferometer, you can see on an object, it's to the order of 10 minus 21, which is very, very small. So in order to have a stronger delta L, you have to build a longer baseline of the interferometer. So you do better with a longer baseline in terms of increasing the sensitivity of your detector to detect a gravitational wave. And to understand a little better, so we'll work out a little bit of the math to understand how we arrive at the final configuration of the interferometer. So what you consider is you have a laser, and then we'll consider the scalar model to define the electric fields. And we'll assume that they're all plane waves. So to start with, if you see that nu is the optical frequency, and then we define the term omega as the optical angular frequency. At the start point where it starts propagation, z is equal to 0, you can define the electric field of a laser given by the equation. And then as it propagates, you can see that at any point z along the direction of propagation, you can define the electric field as given by in the equation on the right side. And then when you work out the math to actually define the different electric fields that are there in a simple Michelson interferometer. So that's the basic math. So you use the same thing to define the electric fields in a Michelson interferometer that has arm lengths LA and LB. So you have the input electric field EN, and then that traverses along along both the arms, and then comes back and then recombines. So what you see in here is actually at the output is actually a combination of the electric fields that come back to the photodetector. So what you arrive in here, if you look at the light intensity at the output port, you can call it as the difference in the electric fields of the arms, and your E out is going to come down to the expression that you see in here. And now the output intensity, which is actually, if you take the modulus of this squared, will give you a differential phase. So the output intensity is then proportional to the differential phase that the interferometer measures. So as you move the differential, as the differential phase moves over 2 pi, you see the fringe pattern or the output intensity going from bright to dark and then to bright. So the whole 2 pi change in tuning the phase of the Michelson interferometer can be seen at E out. So in order to build a detector to detect a particular frequency of the gravitational wave, it is important to know the frequency response of the Michelson interferometer so that you know how sensitive it is to the source that you're looking at, to the kind of sources that you're looking at. For us, we want to stick to a band from a few hundred hertz to a kilohertz kind of range. So in order to do that, so what we will do is we'll work out the frequency response of the Michelson interferometer. So as we saw earlier, we'll define the differential phase. And as you can see, the term that is in the block red, that defines the frequency response of the interferometer itself. So if you have fixed omega, small omega, as the angular frequency of the incoming gravitational wave, you can express its frequency response in terms of the phase difference we see at the dark port. Now, in this expression, if you consider the period of the gravitational wave, which will be given by 2 pi by omega, if that is long enough than the storage time of the Michelson interferometer. The longer the storage time of the interferometer means the longer the arm length. So then the absolute value for this response will boil down to the first parameter that you see, 2 omega L by C. And this means that the phase change that the gravitational wave causes is proportional to the baseline length of the interferometer. So this means that as you increase the length of the interferometer, you're more sensitive to the gravitational wave. But the thing is, we've seen that the frequency response has kind of a 2 pi response from the bright fringe to a bright fringe, which means that as you keep increasing the arm length, you start accumulating the effects of the gravitational wave during the storage time of the photon in the interferometer arms. So as they get integrated and eventually cancel out. So you can actually like maximize or optimize the length of the interferometer for a given frequency of the gravitational wave. And if you consider a 1 kilohertz arm length, 1 kilohertz gravitational wave, this optimal arm length of the interferometer will work down to 75 kilometers. So if you were to use a Michelson interferometer on the Earth to detect a gravitational wave with optimal sensitivity of to detect a 1 kilohertz gravitational wave, then the length of the Michelson would be 75 kilometers along each arm. But that's too long. We know that that comes with a lot of practical issues given with the curvature of the Earth and how large the mirrors have to be if you have to propagate a laser beam for 75 kilometers. So To optimize the interferometer and also keeping realistic arm lengths in mind of a few kilometers, people came up with the idea of proposing several configurations. The first one is the delay line arms you see in here. They are folded interferometer configurations. The first one is the delay line scheme. In the delay line scheme, you can see that the optical path in each of the arms gets folded by reflections at different points on the mirror. And the effective arm length will be the number of bounces it goes through, number of reflections that it goes through before it reaches the beam splitter for recombining. So this has a lot of complications when we have to do it for kilometer long arm lengths, because you need a smooth mirror that is free of imperfections at different over a large area. Obviously, when you start traveling when you extend the arm length to a few kilometers, you have to start increasing the diameter of the mirrors to accommodate the beam. And then you start accumulating losses because of the imperfections at different points on the mirror. So there were some practical difficulties. There are some practical difficulties in actually using this configuration for longer arm lengths. One interferometer does use it, which is the GEO detector, GEO 600. It uses this, so it does 2 bounces. 600 is the arm length, and it does 2 bounces. So the overall length is 1,200 kilometers, 1,200 meters. And then it comes back and recombines at the beam splitter. But if we have to use kilometer arms and try to do this, it's kind of difficult. So the other configuration that was proposed is a Fabry-Perot Michelson configuration. So before we go into deep into how Fabry-Perot Michelson works, it's important that we understand how a Fabry-Perot cavity works. So a Fabry-Perot cavity is basically a simple optical resonator. It has 2 mirrors, and it is defined by the length L, and the 2 mirrors, the properties of the mirrors are given by its transmittivity and the reflectivity. And like we did in terms of the interferometer, simple Michelson interferometer, if we have to define the electric fields at different points inside the Fabry-Perot cavity, you can find what the electric fields are. And then what you see in here, in the plots in here, are the buildup that you get. So depending on the T and R, the transmittivity and reflectivity of the cavity, you can see sharp resonances because it acts as an optical resonator, and you can see sharp resonances that occur periodically, which is defined by the length of the interferometer. The distance between these 2 resonances is what we call the free spectral range of the Fabry-Perot cavity. And as you can see, the phase response also is very fast as you make a round trip phase, because there is a phase change at every reflection. And then once you start accumulating at the point of resonance, you see a sharp phase change in here. So that's a very fast response through your resonance. So you see a very fast phase response through your resonance. And that's very important and makes the Fabry-Perot cavity more effective when we have to incorporate this into a Michelson interferometer. So if you look at the Fabry-Perot optical resonators, you can also define another parameter, which is again dependent on the length and the reflectivity. We define the finesse, which is actually a measure of how sharp of a resonance a Fabry-Perot cavity can create. And we call it the finesse. And as you can see here, it's actually defined in terms of the reflectivity of both the mirrors. And if you have to compare the simple Michelson arm length of 4 kilometers with a Fabry-Perot arm length of 4 kilometers, you can see that the phase response just shoots up. You do much better. And depending on the finesse, you can actually tune the gain that you get in here. And you introduce another parameter, which is called the cutoff frequency, the point where you can see the roll off. And that depends on the finesse and the length of the arm. And this actually like gives us is a very important parameter because beyond this point, even if you increase your finesse, there's not much response that you get beyond that. So, but what you see definitely when you introduce a Fabry-Perot cavity into the Michelson arms is a DC response amplification, which is very good because you increase the sensitivity of the detector. So what a Fabry-Perot cavity does is it stores power, laser power inside the arm, and also allows for accumulation time of the gravitational wave signal, which means it can be equivalent to increasing your arm length of the interferometer itself. So now, if you have to compare the frequency response of the three configurations that we considered, you can see that the simple Michelson falls in the bottom in here. And then you can see there is like one notch because the Michelson has only one bounce. And if you introduce a delay line Michelson, depending on the number of bounces, you'll see several notches that are coming in. And in a Fabry-Perot Michelson, the number of bounces is actually large enough that you can make some approximations and the frequency response becomes smoother for us to handle. So what we see now is actually the Fabry-Perot Michelson interferometer. So if you have to introduce Fabry-Perot arms to your Michelson interferometer, you would see, you will arrive at the basic form of the modern gravitational wave detector. So you use the differential nature of the Michelson to detect, and you also get a longer storage time or gravitational signal accumulation time by using Fabry-Perot cavities. So, but when you see actually the actual interferometer that is being used for gravitational waves, apart from the Michelson arms, you do see a couple of other mirrors in here. And these two mirrors that you see at the input and the output are what we call the recycling mirrors. So apart from the combination of Michelson and Fabry-Perot cavity, we also have introduced recycling cavities in order to do better in terms of sensitivity. And the configuration that we use, we call it the dual recycle Fabry-Perot Michelson interferometer. So you have two recycling cavities that actually can do a better job in being sensitive to gravitational waves. So we have two recycling cavities, so we'll go into the details of each one of them. So the first one is the power recycling, which is done at the input port of the interferometer. So the power recycling is a tool that is employed to actually suppress shot noise. So shot noise is nothing but the photon counting error that you see at the photodetector. We know that we detect the interference at the dark port of the interferometer. And owing to the photon counting error, because light is made of photons, so you arrive at a noise parameter that's called shot noise. And the shot noise level depends largely on the power of the laser that is being used. So as you increase the laser power, you do better in terms of shot noise levels. but you can only increase the laser power so much because of the laser technology that we've been using. So in which case, what we see is, sorry, excuse me. I sort of lost my mouse, excuse me. So what you see in the power recycling cavity is basically a kind of technique that mimics the increasing the laser power levels. So what you do in a simple Michelson is, when you have interference, we always try to configure the interferometer so that there is no light coming out of the interferometer. So the photodetector kind of sees the dark fringe. But in order to conserve, where does most of the light go in your interferometer? It all goes back into towards the laser itself. So which is not kind of ideal, because you're looking for increasing the laser power, and most of your light gets wasted by going back towards the laser itself. So what we use is, we put a recycling mirror so that the reflected light gets used up again and inside the interferometer again. So what we do is, we place the mirror in front of the interferometer, as you can see in here, and this works as equivalent to increasing the input laser power. So if you do that, your light goes back and forth, but where does eventually all the light go? We are not working in the ideal situation. So your mirrors do have losses, and there is scattering that happens at different surfaces along that makes the interferometer. So eventually, whatever power we put in gets lost as mostly optical losses within the interferometer. So our power recycling mirror helps us do better in terms of short noise levels. So it is a very good improvement that we can do to increase the sensitivity of the detector. In another point of view, the PRM, or the power recycling mirror, forms an additional cavity. If you have to look at the whole Michelson, if it is considered to be tuned to operate, to give a dark fringe, you can think of it as a compound mirror which has a very high reflectivity. So the whole interferometer itself can be assumed to be a compound mirror that forms a Fabry-Perot cavity with the power recycling Michelson. So I think I did not mention this earlier, but the interferometer has certain degrees of freedom that it is sensitive to. So one thing is the common arm length change, which means if the arm lengths are increasing simultaneously, the interferometer will be insensitive, but it's still a degree of freedom of the interferometer. And then you have the differential motion, each arm similar to what the effect of a gravitational wave would do on it. So it is the differential degree of freedom. And then you have the Michelson degree of freedom. And then you have the recycling cavity lengths. So these are the various degrees of freedom of the interferometer itself. So if you have to consider the entire Michelson as a compound mirror, what you have in here is defining the power recycled cavity length as one of the degrees of freedom of the interferometer. So if you have a common arm length change in the Michelson, your power recycling cavity would look like a 3-mirror cavity with very high finesse. But if you were to look at it, the differential motion, for example, the effect of an incoming gravitational wave, it would look just like a Fabry-Perot cavity, an arm cavity. So similar to, along the same lines of discussion, if you would think of the signal recycling mirror in here. So you have the signal recycling mirror at the output, And what the signal recycling mirror does is, its role is giving different storage times for the common and differential modes, which means that we are able to tune the response, frequency response of the interferometer as a whole to the incoming gravitational wave frequency. So what you see in here is actually the frequency response of the interferometer as you change the signal cavity recycling length. You can see that the detuning set to 0 is where you start, and then a detuning of pi would be changing the length of the cavity. And you can see as you change the length of the optical recycling cavity, you can make the interferometer sensitive. You can see bumps rising, bumps at particular frequencies for the gravitational waves that you want to detect. So which means that you can optimize the curve shape depending on the noise. So for example, if you see one particular noise source at say 100 hertz, then you can tune the length of your signal recycling cavity to suppress the noise level there by increasing the phase response along in that particular frequency. So this is what a recycling cavity does. People always think that it is actually like similar to the role of a power recycling mirror that allows to increase the laser power or recycles the laser power. People think of the signal recycling cavity also being recycling the signal. It's not recycling the signal, but it is actually like signal enhancing cavity kind of thing. So now, if we bring in the concepts that we've learned so far, we can finally like make sense of what this configuration looks like. This is the final configuration that advanced LIGO is operating in here. So you see the laser in here, and then you see some input optics. So the input optics and output optics are basically cavities that allow for cleaning of the laser light that comes in terms of frequency. So what you do in input optics is we have an input mode cleaner, which is a 3-mirror cavity that is suspended inside vacuum, which means it's more stable than the laser, which sits at room temperature. And then since the arms are suspended, it is immune to the other noise sources, the seismic noise sources around it. And you can cancel out the noise that comes in the laser at those frequencies. And then after that, you have the power recycling mirror in here. And then we have something called PR2 and PR3 in here. So these mirrors are basically folding mirrors that allow for increasing the length of the power recycling cavity to the lengths that they are designed for. So there is a finite distance between the vacuum chamber that hosts the PRM and the beam splitter. So in order to achieve the recycling length that we want, we introduce some folding mirrors to do the job. These are highly reflective mirrors. So those can be ignored and just assume that the power recycling mirror itself can be stretched into a single long cavity. And then we have the beam splitter, and then we have the ITM and the ETM. The ETM are the actual test masses that respond to the incoming gravitational wave. And then we have the ITMs that make the Fabry-Perot arms of the Michelson interferometer. And these actually recombine, and then at the output, you have the signal recycling mirror. And in here also, you have the 2 folding mirrors, SR2 and SR3, which do the same job as PR2 and PR3 in allowing us to get the desired length for the signal recycling cavity. And then you have the output mode cleaner, which does the same job, similar job to what the input optics does. So in case there is scattering or spurious light that leaks into some other higher order modes in the laser, then those get cleaned at the output mode cleaner. The output mode cleaner does a fantastic job of actually reducing this spurious light and put the optimum amount of light on the photodiode and where the gravitational readout comes. So in order to assemble this whole interferometer, there are several subsystems. The interferometer is split into several subsystems. What you see in terms of these abbreviations, you see LSC, which is the length sensing and control, about which you heard more in Dr. Suresh's talk. We have the physical environment monitoring, which looks into the environment monitoring in terms of temperature, in terms of wind speed, in terms of the seismometers and accelerometers and the temperature change from the center to the corner station, from the corner station to the end station, and all other environmental parameters around it there. And then you have the core optics and optical components, and that actually is a subsystem that deals with designing the mirrors, the large mirrors that are being used in LIGO. And then we have the SEI. So the mirrors are held in suspensions, but they are actually, suspensions are mounted on seismically isolated optical tables. So that is what we call the SEI. And then we have the SAS, which is the suspension subsystem. The mirrors are actually suspended as a pendulum. And then we have the thermal compensation system. Because of the large accumulation of a large amount of laser power in the arm cavities, to the order of expected to be of the order of 750 kilowatts, this actually warps the mirror because of the heat. Even though the mirrors absorb only a few ppm, the mirror starts warping. So in order to correct for the radius of curvature, there are actually ring heaters and a CO2 laser that can impinge a heat image on these mirrors, so that you can heat the mirror appropriately and change its radius of curvature to a small extent, to correct for the thermal lensing effects that you see as the power builds up. So that is done by the thermal compensation system. And then we have the arm length stabilization system. This arm length stabilization system, what it does is it isolates the 4 kilometer arms from the rest of the interferometer. As you can see in here, when we talked about the power recycling cavity and the signal recycling cavity, we're bringing in multiple cavities together, which means the light from one gets coupled into the other. So we have a lot of coupled cavities in here. And if you try to bring the whole interferometer into resonance, it's kind of difficult because they're all coupled into each other. So if you can isolate each of them, it is more, it's possible to build them bring them together in a more systematic fashion. And also when they lose out of lock, it is possible to troubleshoot them as well. So the arm length stabilization system isolates the arms, the two arms, independent of the rest of the interferometer. So all you have is first bring the Michelson together and the arm lengths together, and then you bring the whole system together along with the power recycling cavities, so that you can keep the interferometer in a resonance state, useful for gravitational wave detection. So as you've seen the configuration that we've put together, there are actually also different detectors around the world. The configuration that they're being used is what I've tabulated in here. We have the LIGO Hanford and the LIGO Livingston detector in the USA. And the baseline length of this is 4 kilometers. And the configuration in which it is used is the dual recycled Fabry-Perot Michelson interferometer configuration. We have the detector Virgo in Italy, which is a 3 kilometer detector, which is also used in the same configuration. We have the detector Kagra. They're all slightly different. Kagra is a detector that uses cryogenic mirrors. So the mirrors are cooled down to avoid the heating effects that the mirror would have to go through. So you cool the mirrors enough so that you can take away the thermal noise that comes from heating the mirrors. So they are also using the interferometer in the dual recycled Fabry-Perot Michelson configuration. And then we have the GEO 600, which is the 600 meter arm length detector in Germany. And this is one of the interferometers that is not being used in the Fabry-Perot Michelson. As you can see, the arm length is only 600 meters. So a dual recycle delay line Michelson would actually is possible to be employed in here. So that is what GEO uses, GEO 600 uses. So in order to summarize what we've learned, so I just wanted to give one carry home message, which is you've seen the picture of the interferometer, and everybody talks about it being used as a dual recycled Fabry-Perot Michelson. But what is this configuration, and why we arrived at it? Why not use a simple Michelson interferometer? So that is what I wanted to discuss in this talk. So the first thing that we started with is using a simple Michelson interferometer. And what we talked about is how gravitational wave detection depicts itself in a Michelson interferometer. It is actually an optical phase measurement. It depicts itself as an optical phase measurement and is sensitive to the differential degree of freedom of the Michelson. And then when we introduce Fabry-Perot arms in a Michelson interferometer, we are able to extend the baseline length of the interferometer and provide a longer storage time for the gravitational wave signal to interact with the photons, which means that you increase the sensitivity of the Michelson interferometer by introducing Fabry-Perot arms. And then we talked about using the optical recycling technique, which basically both of the recycling cavities allow for different storage times for the light that goes into the interferometer and the gravitational wave signal that comes out. In the power recycling cavity, it is used to maximize the laser power within the interferometer. And in case of the signal recycling cavity, what you see is you are able to optimize the bandwidth of your detector or tune the resonance of your detector accordingly to the kind of sources that you want to detect. So when you are looking for how the interferometer is being operated, one of the important parameters is the detuning of the signal recycling cavity, which says what is the bandwidth of, or how the response of the interferometer looks like. So these are the take-home messages. So that's actually end of my talk. So I'm going to see if I can address any questions. So if you have any questions, please post them in the chat box and I will be able to get to them.
Hello. Hello, Manasa.
Yes, I hear you.
Hi, this is Nishant. Are you taking questions? And
yes.
Okay, yeah. Then I just wanted to announce that after everything is over, then I'd just like to say a few words, but only after the questions are over.
Sure.
Yeah. So I'm here. Yeah.
So I hope you can hear me. So I have one question from Bhuvnesh Bravar. He asks, what could be other methods to detect gravitational waves instead of interferometers? So I think this is there in one of my slides. Let me screen share it. So As you can see in here, we have, we can see that our ground-based interferometers are the detectors that you see on the top right. So these are detectors that are sensitive to frequencies of a few hundred hertz of the gravitational waves, and the sources that we detect are binary neutron stars and binary black holes. One of the other kind of detectors that is being pursued right now is the test for space-based interferometers. There's a project called LISA that actually is working on building space-based interferometers, and they will be sensitive to sources like binary supermassive black hole mergers. And you can see in here that you see there is ELISA, which is the prototype, and then we will have LISA. So that's how their sensitivity curve will look like, and you can see what are the sources that they are sensitive to. And then these are what you see in here, detecting billion solar mass black holes. These are actually array of detectors. As you can see that there are pulsar timing arrays. So they are sensitive to sources that have a frequency of the order of 10⁻⁸, 10⁻⁷ hertz. So Namonil Saha asks, is there a way to use Fabry-Perot arms in space-based detectors in future like LISA? Yes, LISA actually uses a cavity. It's a 2-mirror cavity that is going to be up in space. And you can see the LISA project page for more details. It actually uses only a single cavity. The reason why we use a Fabry-Perot cavity is because of the restrictions that we have in increasing the arm length on terrestrial detectors. So basically, if you have to build an arm cavity for 75 kilometers, you have to dig through the earth, which is practically becomes impossible for us. And also the availability of a land that is 75 kilometers long also. Which is why we have to use Fabry-Perot arms in terrestrial detectors. But space-based detectors, you don't have that restriction as much regarding the length of the cavity. So LISA uses a suspended cavity, 2 mirrors in space, separated by a distance. That is what LISA will be using. So I see another question. At full sensitivity, how many detections do we expect per year or per month? So at full sensitivity, given our current rate, we would be expecting sources being detected every day, sometimes multiple sources every day. So that gives you a rough number of how much we will be detecting. So initially, before we had a detection, we found out that we've been very pessimistic about the numbers. But now since we know the actual number of detections that we see, we are sure that we will be able to see at least a few detections, at least one detection per day of that order, or in a few days of that order. Which is the configuration that is planned to be used in LIGO India, Fabry-Perot, delay line, or something else? So we will be using the Fabry-Perot Michelson, the same DRFPMI, dual recycled Fabry-Perot Michelson configuration. We want to be, so what advantage we have in LIGO India is that we can learn from the mistakes, or learn from what LIGO has learned through building their detectors. So we can so what LIGO basically did was, like, it's a detector that started a few decades ago. And there have been revisions that have happened with the detector, but they have constraints because the building is a few decades old and now we are starting it from the core, we will be able to correct for them better and probably do better in terms of sensitivity. And since we've also learned from the errors, for example, in advanced LIGO, we know that the laser power cannot, they're struggling to increase the laser power. And also they have a few hurdles in terms of having spurious higher order modes being resonant in the detector. So they can do better in terms of the mirror polishing and things like that. So those actually are few lessons that LIGO India can learn from the detectors in the US. So those will be taken into consideration. And can LIGO be used to detect dark energy or dark matter? How we know the polarization of G waves and what is its significance? So the way that we've been we've been using multiple detectors, which is why the more the detectors, the better. So as you see, the response of, if you look at the antenna pattern for the gravitational wave in two orthogonal polarizations, for a particular detector, you see it's a kind of a lobed pattern. So the response of your detector is very much dependent on the polarization of the gravitational waves that comes through. If you're going to have a gravitational wave that is propagating along the plane of the detector, it might even go undetected because the response of your detector is very low. And depending on the position of the detector, since we have a network, depending on the position, the response that you see at different detectors will be different, and that will give us information about the gravitational source and its polarization. Let me see if there are a few more questions that popped up. Did I miss any? Why we have ripples at the higher frequency in the phase response graph for a 4-kilometer Michelson interferometer? So the Michelson response that you saw has only one notch. It doesn't, the multiple notches that you see comes from each of the reflections from the mirrors. So every time you if you reflect off of a mirror, there is a phase change, and that is why you start seeing the notches. And since this is a log plot, you see the notches coming closer together. If you have to, so in case of the 4-kilometer arm length, you see that there are two notches, which means you have two reflections. In case of the arm length extended to 75 kilometers, you can see that you have this kind of exponential behavior. If you work out the frequency response, you have this kind of exponential expression that arrives, and that gives rise to these notches in the frequency response of the Michelson. Is there any other question? I see a few questions regarding, I do see a few questions regarding CMB measurement and things like that, but I'm not the expert to answer those. So I'm not going to take them. So. Nishant?
Yeah. Hi, Manasa.
I think we've exhausted the questions that have been posted.
Okay. Yeah, so I just want to say a few things. This was the last lecture in the summer school. So I want to just say a few remarks on behalf of the organizers, Professor Paranj, Professor Surhud More, and myself, who have been actually quite happy with the response and would like to first thank the students who have been joining in large numbers through the Zoom as through our YouTube. Um, the person who is most responsible and have been diligently making all the YouTube videos available is Divya. Is a PhD student working with Professor More at IUCAA. He has really done a very painful job of connecting through every single lecture and has been doing fantastically good. So we all would like to thank Divya for the great effort he has done. Thank you, Divya. Um, um, and then we would like to thank Dhruba Saikia from TLC and all the TLC staff for helping us with the refresher course, taking care of all the evaluation process and helping us with various other fine details, and also for taking good care of question answers through the YouTube feed. So thanks to Professor Saikia and the staff from TLC. We then would like to also thank very much to all the lecturers who have taken their time, given lectures in these summer school. None of this was, of course, possible without them agreeing to these lectures and giving some special situation with coronavirus and everything. I hope you're all staying safe and have heard from the various experts in astrophysics and astronomy through these lectures. And then none of this was also possible through the various technological support. For example, Zoom and YouTube and various things. This was all a challenge for many of us because this was not seen before to conduct such an online course. And for that, we also thank our staff from the Computer Center, Santosh Jagade and Sagar Bhosle, who have been really working hard in the background to make all things go very smoothly. So thank you, Santosh, and thanks very much, Sagar, for dealing with all the Zoom and various queries. And finally, again, thanks to all the participants, all the lecturers, Divya, TLC staff, Santosh, Sagar, and the team of organizers, especially Professor Asim Paranjape and Professor Surhud More, whose experience have been very helpful in conducting these. And finally, would like to also thank our director, Professor Shomak Rai Chaudhary, who have been always very helpful and supporting in all these efforts. So thanks to him very much.
Nishant, one thing, sometimes people ask for certificates and also.
Okay, so to certificates, all as we have clarified in the emails, and I would like to reiterate that we are simply unable to provide any certificate. The reasons have been somewhat clear. See, the main reasons for granting certificates have been the close discussion and contacts with